In 16C, what we do is we determine some normal probabilities. We've already done this using the 68, 95, 99.7 rule and some integral calculus, but we'll use some other features of the calculator today to do this. So we can use statistics or spreadsheet in menu or main screen, and then interactive or action. Now this is my preferred method, is via interactive, and this is the way that I'll go on to explain it. So in all of these questions, you want to use distribution continuous on the new calculator. That really doesn't need to be there because the old calculator is non-existent. And then use normal PDF if you want to graph it, and CDF if you want to calculate. All right, so I'll go on to explain how this will work. So in the first question, what we'll do is we'll sketch a random variable x is normally distributed with a mean of 6 and a variance, okay, a variance of 4. Okay, so again, really important to note that that's mu, okay, that's the expected value or the mean, and that is sigma squared, that's the variance, okay. So let's have a look at what this might look like on a curve. So I'm going to go and now use normal PDF to graph the distribution. I'm going to go to interactive, distribution. It's a continuous distribution, and we're going to use norm PDF. All right, what we do is for x, we use x. Now what we do is, this is asking us for the population standard deviation. So the calculator is not really well designed to work with the standard format that we write these things. So first of all, the calculator wants sigma, which is the standard deviation. So what we're going to do is note that the standard deviation is going to be sigma squared square rooted. So it's 4 square rooted. So that's going to be 2. And the mean or the expected value is 6. All right. So what it's going to do, you're going to hit OK now, and it's going to go wrong argument type, and that's fine. That's fine. So what we're going to do is edit and copy this and hit graph and table. You can see here I've had a go at this earlier. So I'm just going to dump this and get this back to a default Cartesian plane. All right, so now what I'm going to do is ask it to graph it. And we get this fairly mediocre looking straight line with a little bit of a bump over here. Now what's it done? Well, what it's doing is it's attempting to graph it. Understand that its mean is going to be 6 and the standard deviation is going to be 2. So that means that if we consider how we're going to adjust the scale, 6 is the middle, and it's going to go 8, 10, 12, 4, 2, 0. Okay, so we're going to get a curve that goes like that. So to see this thing, we're going to have to extend the x-axis to 12. Now note that the area under this curve is equal to 1. So the maximum value is going to be really low, like 0.1 or something like that. So let's hit the 4 arrow button and start to play with our settings. So I'm going to go an x-min of, let's go -2, up to a maximum of 14. So I'm going to go a bit beyond the 3 standard deviations. I'm going to 4 standard deviations, that's fine. I'm going to change the y-min to 0, okay, that's the lowest value that can come out of it. All continuous curves are above the x-axis. And a max value, let's go 0.2 and see what happens. All right, we got it. So there is our curve right there. Let's extend that y value up a little bit higher, 0.3. Okay, so there's our first one. Right, now what we're going to do is compare that to the second curve. Okay, so we've sketched this one. All right, this one here is another curve for the variable, random variable y is normally distributed with a mean or expected value of 6 and a variance of 9. So that means that its standard deviation is 3. So I'm going to adjust this to 3. Now what this should do to my graph is basically pull on these endpoints. I don't know, you obviously can't see what I'm doing now, but I imagine with my hand holding this point here and this point here and giving them a pull so that this middle value will come down. Okay, so that's what's going to happen. What it's going to do is stretch it out, bigger spread, higher standard deviation with the expected value still at 6. So what I'm expecting is a curve that is more spread out with its highest value lower. All right, let's see if that comes to fruition. It does. Okay, so imagine grabbing those two bits, pulling it, and this part has to come down. Now remember, it has to come down because it has to preserve an area of 1 underneath the curve. Okay, it can't be the same height pulled out longer because then it's going to have a larger area. So because it has a larger area here, what it does is it pulls down this point here to make sure that it preserves the area of 1. Okay, so let's have an answer to this question. So what's the difference between the curves? So curve 2 is more widely spread, but lower max compared to curve 1. This is because curve 2 has a larger standard deviation, implying larger spread around the mean. All right, so that's basically what happens. All right, let's answer a few more questions. Very rarely do I graph it, girls. So yeah, I'm just copying, or I've copied Mr. Tench's notes for these, and I think it's important to know what the graphs look like, but I hardly ever, if ever, use the graphs to answer the questions. All right, so the distribution of Navy officers is found to be normally distributed with a mean of 175, standard deviation of 5. What's the prob that a randomly selected Navy officer has a height less than? Yep, okay. Do these questions approximately using the rule and then use the calc to find it. Okay, so let's do that. So what I'm going to do is answer A, B, C, D, and E using the rule and then calc. All right. So let's break it up into two parts. And as with all normal distribution graphs or questions, I would graph the thing. It has a 175 mean, standard deviation of 5. So 1, 2, 3, 1, 2, 3. Again, it doesn't have to be perfect, just enough to visualize 190, 170, 165, 160. Okay, so there's 3 standard deviations either side of the mean. Okay, so we want to know the probability that the height is less than 175. So here's 175. We want to know the chance of it being less than that. Now, if the total probability under this is 1 and the normal distribution curve is symmetrical, this one has to be 0.5, okay, or 50%. Now let's confirm that with a calculator. So what I want you to do when you write your notes on this section here is make sure that you write down the calculator syntax. That's going to be really important. So we're going to go to interactive distribution, continuous distribution, and we want normal CDF. Okay, that's cumulative. All right, what's our lower value? Our lower value is actually negative infinity. Remember, this curve goes or extends infinitely in the negative direction of x. So we're going to say that this is negative and infinity appears in math 2. There it is there. All the way up to its upper value is 175. And what it does is it basically cumulatively adds all the little bits of areas together from negative infinity up to 5, thus giving us the area under the curve between negative infinity and 175. Now I know that the answer has to be 0.5, but let's just see what it says. Now sigma is the mean, the standard deviation. Be careful, okay? So it's the standard deviation, which is 5 in this case, and mu is 175. So again, this has to be, it has to be 0.5, and it is. All right, so let's do or note that. So it's norm CDF, negative infinity, 175, 5, 175 equals 0.5. So that's how I do it on the calculator. Okay, between 170 and 180. 170 and 180, that's 0.68 because 68% of the population fall within one standard deviation of the mean. Okay, so norm CDF. Now what we're going to do is just change this. Instead of negative infinity, we're going to give it a lower bound of 170, an upper bound of 180 with the same mean and or standard deviation and mean. And this has got to be 0.6, but we're going to be a little bit more accurate this time. So it's going to be 170 to 180. 0.682 ... depending on the number of decimal places. All right, I just got interrupted. I'm actually recording this while the year 10s are working away, so I might get people jumping on the meet spasmodically. All right, so we've got a height between 165 and 185. So there's 165 and 185. That's two standard deviations either side of the mean. That's going to be 0.95. All right, but what if I asked in a SAC question for a 3 decimal place approximation? Well, the 68, 99, 99.7 rule is no good. So we're going to use norm CDF, and we're going to go between 165 and what was it? 185, 175, and it's going to equal 0.9. And let's just see what happens from here. 165 to 185, 0.954 ... So I would ask for a 3 decimal place approximation for that if I was in a SAC. Right, height greater than 1.9, so 1.9. So this part here is half of the stuff outside 3 standard deviations. That's going to be 1 take away 99.7 all divided by 2, which is going to be 0.3 divided by 2, which is 3 on 20, or what is it, 0.3? 0.15, okay, so 0.15. Now let's try that on the calculator. So I'm going to go and start at 190, and I'm going to go up to positive infinity because it's 190 and more. So keyboard and infinity. 0.13. What did I say? Three over 20. Yikes, why did I get that wrong? Height greater than 190. There's 190. So it's going to be 100 take away 99.7 divided by 2. It should be 0.15. What have I done wrong? Yeah, it is right. So what happens is this is a percentage. So I divide that by 100. And that's going to give me 0.0015, okay, as a probability. All right, so that's going to be the percentage. All right, so 3 over 20, but 3 over 20 divided by 100. And so that is going to be 3 over 2,000, which is equal to 0.0015. Okay, and when I do it with normal CDF, I'm going to go 190 to positive infinity, 175 equals 0. So you see the precision of that, it's pretty bad. The 99.7 rule, 134 ... Okay, E. So we're going 165 to 180. So that's going to be 0.64 plus 0.135. So 0.64 plus 0.135, because this part here represents 13.5%. Again, go look at your diagram on a previous page. So that's going to be 0.64 plus 0.135, 0.775. All right, again, let's check that out with norm CDF, which is the one you should be using, not this approximation rule, unless it tells you to. 165, 185, 175. Oh, fingers crossed. Let's see how it went. 165, 180. Oh, great. It's 13.5. There's my mistake. All right, so I said 0.64, it's 0.68, because it's the 68, 99, 99.7 rule. So good one, Mr. Miller. So let's just tweak that to be 68. That's better. All right, and then this one looks a hell of a lot better. I was going to say, like, you know, I know that, like, it's not exact, but that's way off. 8, 1, 8, dot, dot, dot. All right, so 815 compared to 818 as the exact value. All right, so again, I'd be using the normal CDF version of that to get an exact area rather than the rule. But it does show you the correlation between these two, that there is, they're pretty close to each other, and that's because the 90, 98, 95, 99.7 rule is approximations of the area. Can't believe I did that 0.64 when this is mentioned here as well. Anyway, we'll get over it. All right, suppose that Z is a standard normal distribution variable, has a mean of 0, standard deviation of 1. All right, so let's just define it. So Z is normally distributed with a mean of 0, and remember that this is sigma squared. Okay, so that's going to be 1 in this case. Okay, so for this first one here, we're going to get the probability that it's between, the random variable is between -1 and 2.5. So on a normal distribution curve, that will be, what we got, a mean of 0, 1, 2, 3, -1, -2, -3. All right, so what we're looking at is between there and there. So we want this area here. All right, so what we'll do is just go over to interactive, distribution, continuous, normal CDF. Our lower is going to be -1, our upper is going to be 2.5, where we've got a standard deviation of 1 and a mean of 0. Okay, so that one there equals, and so I'm just going to write the calc syntax, norm CDF, -1, 2.5, 1, 0 equals 0.835135 dot dot dot. VCAR typically use 4 decimal place approximation, but depends on the question. This one here is Z greater than 1, so we want this part here. Now that one actually we could get a good approximation for by using the 68, 99, 95, 99.7. So that should be 0.5 plus 0.34. That's 68, that means that's 34. So this is going to be that removed from 1, which should be 84, which will equal 0.16. But let's do it using norm CDF. And we're going from 1 to positive infinity for a standard deviation of 1 and a mean of 0. So 1 positive infinity, all right, equals 0.1586 dot 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 dot. Okay, last example. Find the probability that the random variable is less than 32 if x is normally distributed. So again, important to note the distribution, with a mean of 28 and a standard deviation of 1.7. So again, what we're looking for here is we've got a 28. Okay, and there is 1, 2, 3, 1, 2, 3. They should be separated evenly, but just drawing the picture. So 28, 32 is somewhere here. We want this area here. Okay, so for A, we're going to use norm CDF to get it to add all those probabilities together under the curve. It basically just integrates the function. At the back end, that's all it's doing. Okay, so we'll go interactive, distribution continuous, norm CDF. Our lower is negative infinity. Our upper is 32 with a standard deviation of 1.7 and a mean of 28. See if you can actually do a bit of guesswork and see what it's going to be. It's going to be a fair bit of it. I reckon it's like 0.8 or something like that. Heaps of it, right? Because of course, that's 2, 2, 32. It's almost all of the curve, okay? So yeah, negative infinity, 32, 1.7, 28 equals 0.9906 dot dot dot, depends on the number of decimal places. Right, find the probability z greater than, so that's on the standard, and here is one standard deviation above. They want more than zero, so more than half a standard deviation. So the answer has got to be less than 0.5. I'm going to guess 0.4. Okay, so let's do it. B. So interactive, continuous, normal CDF. All right, our lower is 0.56. So I know it says it's greater than and equal to, so we're going to include it. But even if it was greater than, we still include the value itself, because remember, if I integrate for x is equal to 32, the area is 0. So less than and less than and equal to are exactly the same thing when it comes to continuous prob. Our upper is positive infinity. And our mean is one standard deviation of 0. All right, so norm CDF. Okay, so find random variable is greater than 14 or greater than or equal to 14, and we've got that. All right, so let's do it again. Okay, so our lower is 14, our upper is positive infinity. Now, many students will just slam in 12 and 9 in order, 12 and 9, but remember, our mean is 12 and our standard deviation is 3. Oh, but it says 9 there. Remember, that's sigma squared. Okay, so we've got to square root that thing to put it into our calculator. All right, so that is norm. My dog is barking at a bird while recording this video. Hopefully it's not too annoying. All right, let's do this last question. I actually did record it after telling off my dog for barking, and then forgot to hit play when I was recording, and so I was basically recording nothing there. Let's finish this off. So we're working or finding out the probability that the random variable, which is the standard normal distribution, is between negative 1.25 and negative 0.12. So 1 to the left is there, and 0. What have we got? 1, 2 to the left is there. So we're going to be looking in this area here. So we can sort of guess that it's going to be about 0.3 or something like that. Okay, so we're going to run norm CDF again. Remember that it's less than and less than, but we actually can include those values themselves, because if I integrate directly at that point at negative 1.25, I get an area of 0. Okay, so I can actually take it from that point. So we're going to go to interactive. Again, it's really good idea to go through interactive because it tells you the order of the arguments and what it's looking for. So lower is negative 1.25, upper is negative 0.12, and we've got a standard deviation of 1 and a mean of 0. Okay, so negative 1.25, negative 0.1210 equals 0.34659 dot 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 dot, depending on the number of decimal places. All right, and there's your questions.